Hello and welcome to my presentation for my MSc research project, which I've done under the mentorship of Samad Ahmadi. So the research question was to investigate whether it was possible to identify the owner of a smartphone via their typing signature. To do this, I've set out four major objectives. First, to gather a set of typing features, identify a suitable model, reduce the dimension of these features, and assess the misclassification. The rationale behind this research was that smartphones are the most singular, most used personal device, and it is very commonly shared with other persons, and it is tightly coupled with personal information, corporate information, as well as billing information. So a situation can be where a parent lets their child to play with the smartphone, but then the child would inadvertently concede to some in-app purchases. Or else you share your smartphone with a friend or colleague and a notification is displayed, but that notification could contain some sensitive information. So in the aspect of authentication, we usually have four major factors: what you know, what you own, who you are, and where you are. And these generally manifest themselves in terms of PIN codes, passwords, swipes, fingerprint, and facial recognition, which are all active modes of authentication. What we have done is we've investigated the types of activity on a smartphone, which are generally typing, swiping, and hyperactivity, usually associated with gaming. We shall be focusing on typing activity and as a form of passive authentication. So the idea is that whilst typing casually on the smartphone is continuously authenticating the user. The concept of keystroke dynamics was invented in 1975 and generally makes use of the dwell time intervals and flight time intervals. Yet we can improve the accuracy of this technique by also making use of the touch data such as the surface area and pressure. So I set off to create a typing test for a smartphone, gather the keystroke time intervals, the touch data, and then finally attempt to classify the user. The typing data was gathered from the 100 million British typing corpus, specifically a lemmatized list by Adam Kilgariff, who generated statistics for the frequency of terms. What we've done is we have taken the 5 most frequent terms per length from 2 letter words till 13 letter words. We also added 15 questions to ask users to type, thus recalling from memory rather than copying. So we developed a custom keyboard which allowed us to gather the touch information, and a small app where after a simple typing test, a user would input the words per minute and type the words that we've selected. The digraph features are essentially the time intervals when typing from one letter to another. So the word there, THERE, is split into 4 digraphs, and there are 6 time intervals per digraph, as depicted here. Since for every key we have 2 events, pressing the key down and key up, then you have the intervals for the second key. We also took note of the touch information where we registered the XY position when the user presses down and when releases. We also registered the surface area. The smartphone that we had did not have the pressure feature available. What you have at the lower right is an illustration of the heat map of one specific user. The idea is that when we compare heat maps across multiple users, you can see certain similarities, but also we can also notice certain distinctive features. After gathering the data, we underwent a data cleaning process and some exploratory analysis. We had 32 research participants, where 31 generated 52% of the data, and the 32nd generated 48%, representing the owner of the smartphone. Unfortunately, 12% of the data was lost due to mismatches when linking the touch and click data. In all, there were 2000 events per typing session. The next phase was to do some hypothesis testing to determine whether the mean finger position for each keyboard key for each user had a statistical difference, the mean surface area, the slide distance, and the slide velocity. We determined that the null hypothesis was not rejected for the surface area when releasing the key event, thus this feature was not used. From that, we could come up with 47 features, amongst which we have the phrase length, phrase duration, the keys, the digraphs, the XY position, the surface area when pressing down, the slide distance, the velocity, and we added also statistical features such as the mean, standard deviation, and median for the surface area, the slide, and velocity. We opted for a multi-layer perceptron neural network, and the target was a binary classification on whether the current owner was the owner of the smartphone. We used 30% of the data sets, and for 4 different combinations of activation functions, testing from 1 to 50 hidden neurons, and we did 3 test runs per combination. What we did is we started with 10 features limiting to digraphs, then we added the XY position, we removed the XY position and added the surface area, removed surface area, added the slide velocity, removed slide velocity, added the slide distance, and then one final dataset with all features, all 47. And we found the ideal combination for each dataset. Then what we did, we underwent a k-fold cross-validation technique where we used 70% for training, 30% for testing, and 10 folds, thus ensuring that every single entry is used for training and testing. Here we can see the results by other researchers compared with ours. We can notice that from our research, the slide distance is the most relevant feature, improving the accuracy from 74% to 86%. Yet the best output is obtained when using all features, getting an accuracy of 95%, a false alarm rate of 6%, a false rejection rate of 5%, which compares very well with other research which is limited to just use of digits and for the PIN code. What we did next was we made use of principal component analysis to reduce the number of features, since 47 features could be very computationally intensive on a smartphone. And what we did, we experimented with the Kaiser rule, the scree plot, and the cumulative proportion to determine which eigenvalues we can use. What we can see is that the first 23 eigenvalues components could be used if we use the scree plot rule. If we use the Kaiser rule of considering those components which have a variance higher than 1, then we would take the first 11 components. Thus, we created 2 datasets, one with 11 principal components and another with 20. We identified the ideal architecture and obtained the below shown statistics, where we can see with 20 principal components we get an accuracy of 90%, and the false rejection rate from 5% goes up to 9%, which is pretty positive, considering that we are classifying from just 2 keystrokes. Then one would consider a point and reward and penalty system for the final prototype. We tried to investigate whether there was any correlation in terms of the phrase length, the gender, age, handedness of misclassifications, but we could not find any relevant pattern. We are recommending that this research be extended to pressure-enabled devices, make use of smartwatches and additional features such as heart rate, skin moisture, skin temperature. We strongly encourage adding number of samples per user and considering larger typing dataset. This research can consider also investigating the different typing signatures across different activities, the variance between typing with one or both hands, research in keeping the typing signature across different devices, and during different activities such as gesture activity and hyperactivity. Thank you very much.